All right. Hello, everyone. Welcome to the second session of our Spring 2025 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who are new to VISIM, it is a virtual symposium hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Jesus and Giorgos will be presenting their work. Each presentation should be about 20 minutes long, after which we will take questions from the audience. People can speak their questions or send them using the chat. I'd like to point out that this meeting is being recorded and will be made available shortly after we finish. Thank you all for attending. Our first, yeah. Our first speaker is Jesus Osorio. Jesus is a PhD candidate in the Department of Civil and Environmental Engineering at the University of Illinois, Urbana-Champaign. His research focuses on the design, planning, and operations of shared mobility, public transit systems, and freight logistics. Specifically, he has focused on developing models to address the planning and operational challenges of battery-dependent shared micromobility systems. He has also worked on optimizing intermodal freight networks, exploring alternatives for last-mile delivery, and developing models to optimize freight on transit services. Additionally, he has worked on advancing statistical models to quantify socioeconomic disparities revealed by the way the COVID-19 pandemic disproportionately affected vulnerable and disadvantaged communities' access to public transit systems. Through his research, he has developed a deep interest in how emerging freight and passenger mobility solutions will integrate with existing systems and infrastructure to enhance the efficiency and sustainability of both urban and rural environments. Jesus, I'd like to hand it to you to start your presentation.
Yeah, thank you. Thank you for the introduction. I'll just share my screen real quick. I hope you guys can see it. Is it working well? Can you guys see the? Okay, great. So thank you for that introduction, Kyle. I'm a PhD candidate at UIUC, and this project is titled Planning Service Protocols for Extra Long Trains. This is work that was published last year and that I did in collaboration with my colleague Xiu Shen and my advisor Yanfin Ouyang. So just to start, to provide a little bit of context, we know that the number of mega cities are on the rise. So mega cities are cities of over 10 million people. And we know that from the 90s up to 2016, the number of mega cities around the world actually more than double. And by 2050, it is estimated that about 75% of the population will be lived in urban areas. And why do we care about this type of statistics? Is because very dense aggregated urban areas have high dependence on public transit, specifically on subways and metro systems. So, but this hypercongestion can lead to various negative effects, such as stress and anxiety for passengers because they're in enclosed spaces with a lot of people. We have also increased perception of time. So people actually perceive times in crowds to be, research has shown, about twice as long. There's also a risk of accidents and health conditions for crowded environments, and also people falling into the platforms or rail systems. And then there's other things such as almost like much unintended or unexpected, which is traveling backward behavior, which is when people are traveling away from their destination just to board a station that is less crowded so that they can go to their destination. So if you're going to downtown Chicago, you first take a train to the suburbs so that you can further go into downtown. So this is definitely something that we don't want in our transit systems. So some of the potential strategies that we use and practice to try to mitigate this are timetable optimization, where we try to optimize the schedule of the trains. We also use, we can control the flow of passengers into stations. So studies have played with the swiping cards timing of opening the doors. And if you slow down by a few seconds, you can actually mitigate some of this congestion. But of course, that has its limits. Then there is surge pricing, making tickets way more expensive during peak hours. But this is something very undesirable specifically for transit systems, because we would want people to be using transit. And then, of course, we have expansion of infrastructure. If the current infrastructure cannot handle the current demand, maybe we can build more stations, more rail lines, expand the station capacity. But we know that this is very restrictive, or is becoming increasingly more restrictive, because the cost of infrastructure has significantly increased in the past decades. So this is just some examples from the US where some of the top projects have even over $1 billion per mile in terms of building subway and metro infrastructure. So this has become increasingly more restrictive. So the question is, are there any other ways that we can improve train services without having to touch the infrastructure, or at least build new infrastructure, or in scenarios where all of the strategies that are mentioned are limited? And as you might guess it, the answer is yes. And it's specifically this extra long train idea. And extra long trains, all extra long trains are just trains that are longer than the station platform. So every time I say extra long train, it's just simply that they don't fit, all of the train doesn't fit in the platform. That's the whole idea. But how does this help? Well, I'm going to give an example for a simple protocol where you can have a rail line and you can categorize stations as type A or type B, and then you might have a train where the train is a third longer than the station, and then for type A stations and type B stations, it just shows up, the train aligns the front half or the front 2/3 of the train in the A station, and the B stations you align the rear half, or the rear third, I should say. So in that way, more people can board the train at a given time, but you just need to know which section of the train you need to board according to your destination. And then to show how this might, to more systematically how this might help, I'm going to introduce kind of a tool that we use, which we call the station block diagram. So I'm going to show a plot where the stations are going to be in the vertical axis, and I hope you can see my mouse. So the stations are in the vertical axis, and then the horizontal axis is the configuration of the train. So for regular trains, this is how it looks. You just have one block, one big section that shows up at every station. But in the protocol that I just showed, the A and B stations, it will look something like this, where the train is split into 3 blocks or 3 sections, and only 2 of them actually fit in the platform. So you can see actually the ones highlighted in gray are the ones that would stop. And this diagram is very useful because you can easily see where the extra capacity, which origin and destinations receive extra capacity. In this case, for the even passenger station going to an even passenger station, and odds to odds. And as you can imagine, you can actually plot many protocols. You can have even longer trains that are divided into 4 sections, and in which only 2 of them fit at the station. And then you can keep staggering them like that. And then you would add capacity I mean, the diagram will show you basically what origin destinations you're adding extra capacity on. These were first proposed by Professor De Ganso a few years back. So we were saying so this protocols shown in this diagram only uses one type of train, where the train simply gets staggered, and then every person that goes into the station only sees one type of train. However, we wanted to generalize this idea for any type of demand distribution and any kind of train length. So we kind of introduced the idea of train types to further generalize this protocol. So a train type is just simply characterized by the stopping pattern. So the 2 protocols that I'm showing here, the FR and FTR, are simply protocols that use one train type. They only have a one stopping pattern structure through the whole line. But multiple trains might be able to serve the same station. So we just assume, for instance, that if you have a plot like this, where we have 2 trains with distinct patterns, you can have 2 or 3 train types, and you can actually plot them in the same diagram. And then you can see actually what options in terms of passenger paths they would have. The orange here is just simply a passenger that is performing a transfer to the following train. So we just assume that these services operate periodically, where you first send the train number 1, then number 2, then number 3, and so on. And each train can have very distinct lengths and patterns and stopping patterns. So, and you can see probably where I'm going with this. You can have any number. I can just keep doing this, right? You can just keep adding trains, keep adding partitions to the trains, keep adding length. So it is a very combinatorial problem. So here is where we kind of come up with our research questions given this protocol. So given this kind of generic protocol that I have on the side, the questions are, how many train types do we actually need for quote unquote an optimal service? And then how, even if you already have the train types that you want to serve, how do you determine the size and positions of the blocks or the sections of the train? Every time I say blocks, it's just a train section. You can also think about a section of the train. It just simply means that all the rail cars in that block will open the doors at the same time. So blocks or section, it's just blocks, it's just in the rail industry. So we decided to use that language. And then there's other questions such as, once you have the partition of the train, what part of the train is going to be aligned at what station? So there's a train alignment problem here. Then you have what schedule should the trains follow, given that some of them might change schedule due to their restricted lengths and new accelerations, etc. And then the key question is that now, including all those questions, we need to really couple it with passenger demand. How do we maximize this protocol for any given demand distribution? So this is all generic equations, very combinatorial questions. So this is where I'm going to jump into how do we grab this system and quantify it and try to optimize it. So before continuing, I'm just going to talk about some of my notations and assumptions. We first just look at one directional metro line for this project. And we assume that the demand profile is given as an input. So think about like a morning commute, morning rush hour. Those demand patterns, given let's say from 7 to 9, they're kind of very predictable. People have to go to work, and we have historical data that would give us some predictable demand patterns. Then we assume that the trains cruise at a constant speed, and they have constant dwell times at the stations. So some of the input parameters. So this is where I'm going to go a little more into the notation, so bear with me. We have a set of trains that we want to dispatch. Each train will have a set of blocks. And you can imagine a set of blocks is just simply the maximum number of partitions that you would want in a train. Then you have the set of stations that you want to serve sequentially. And then you have a set of OD pairs, each which has quantity, how many people want to go, for example, to downtown. And every OD pair with a given number of passengers will have an origin station and destination station. And very key is the length of the platform. Every platform, every station will have a limited length. So how do we go about optimizing the service? So first, I'm going to go back to this diagram. So this diagram kind of is very complete. It gives us a lot of information about the protocol. So we can actually base our network based off of this diagram. So imagine now that I look at this protocol, and then instead of looking at the rectangles, I just put a node to represent each block in the network. And then I now say that a node is an active node if it aligns with the platform at a given station, or inactive if it's just hidden at a given station. Then you can look at this block dimension that you have in the horizontal axis, and then you can make it, basically I'm just making it look into the screen, and then you can add the time dimension. So now the protocol can be categorized by this sequence of nodes moving forward in time, which represents the train movement and the alignment at a given station. So you can now add back the passenger flow and the possible links. And here we have the same protocol that we had before, but we have transformed it in this three-dimensional, what we call the space block time diagram. So as you can imagine, this is just a network design problem where the typical network design problem is just, you just want to locate facilities and make flow go through those facilities. But here the facilities are just train alignments in a station in this type of time space diagram. So once we build this network, we simply need to see what is the optimal flow and a stopping pattern of passengers. So, and as you can imagine, every node in this network is it's uniquely identified by a tuple KTS, where the K is the kth block of the tth train at a given station. So these are the three dimensions that we're talking about. And then there's two types of edges in this network. There is the diagonal edges, which are the boarding edges. So diagonal just means you are staying in your same block. And then you have the horizontal ones, where you might transfer to a train that is coming later. So you stay at your same station, and then you transfer to a following train. So, and now that if you're familiar with network design problems, then you know that you need to decide the capacity and the flow going through the facilities. So we have three key decision variables in this three-dimensional network. One is the number of rail cars in a block. So this is kind of how wide is this section of the train, how many rail cars would be included. And you can think about in network design problems, it's just the capacity of your facility. Then you have a eta KTS, which is we simply make it equal to 1 if a node is active or not, which just means that block aligns with the platform. And then we have an X variable, which is the flow variable for a given origin and destination, so that we can know what paths. So we just ensure that all of the origin destinations and their respective magnitudes are served. Then I'm not going to go into the details on here, but then the auxiliary variables helps us keep track of the trains, train times and timetables, etc. So I'm not going to go into details here, but then we can actually formulate the model where we're trying to minimize the number of rail cars that we use in all of our blocks and the travel time of passengers here on the top of the screen. And then with the third term, again, I'm not going to go into details of every part of the model, but just to give you an intuition, we're just trying to serve the passengers for a given demand profile with the least amount of rail cars and blocks. And if you're familiar with this, then you know that you will need your passenger flow conservation constraints through the network. Then you have capacity constraints. Basically, you only the number of passengers that can board a block has to be less than equal than the number of passengers that fit in the block. Then you have some transfer and boarding and alighting constraints. So passengers can only board a train if the node is active. And then you have platform length capacities. Essentially, if multiple blocks open the door at a given station, their combined length should be less than the platform. Then you have some other, the time dimension I'm not going to kind of explain to in detail, but basically we also keep track of the headways and timetables with other constraints, but I'm not going to go here. But the beauty of this is that for real world transit systems, we can actually solve this to optimality. So I'm just going to show some results from our case studies where we actually were able to apply these extra long trains to show how much more capacity would we be able to serve, how much more demand, I should say, with extra long trains. So we look at one of our case studies in Beijing, China, in the subway line 5, which is one of the most congested ones. And this is the demand profile with 23 stations. And this is just the origin destination matrix. And then we actually were able to increase the capacity by 126%. That is more than double the capacity of regular trains for the peak hour. Then we also tried it into Santiago, Chile, where it's a 27 station line that is one of in their metro system with a very distinct demand pattern, as you can see from Beijing to Santiago. And then we actually are able to still increase by 112%. So this gives a lot of hope for this type of implementations in the real world. And if you're curious on how the protocols actually look for real world examples, this is kind of how they look like. I don't expect you to follow every little detail here, but you can see that they kind of become a little more complex where trains might be split into many blocks of different number of rail cars. And then there's just very distinct patterns, similar to before. We might have several options. We know that they're not unique, these patterns, because based on our sensitivity analysis, we can actually have different protocols serve the same demand. But then I don't have time to talk about here, but the sensitivity analysis showed that the operator might have different priorities. So different protocols that are simpler partitions might be also feasible to serve similar demand. And for those of you who might be experts in rail, maybe you're thinking, oh, well, it's okay that more people board a train, but then longer trains actually take longer headways. So it doesn't matter if you have more people in trains if every train actually requires an hour of a headway to actually pass. So actually, we actually do correct for the headway. We have the headway correction factor, which means that we add a penalty for every extra rail car from the platform. We add some penalty to it, and we do some sensitivity analysis from it. And from practice, I mean, the kind of the more selling point that I already told you, that we increase capacity by more than double, 112%. That is assuming that extra long trains would run at the same frequency. But in practice, actually, from the railway capacity manual, we know that this penalty is more in the magnitude of 0.01 to 0.02 minutes per extra rail car. So we actually expect realistically that the benefit in the real world would be more about 60%, about 50 to 70% increase in the demand that regular trains can serve. And then for other numerical experiments, I'm not going to go into details in any of this, but it's just if you're interested in exploring some of the paper, we also do more robust testing where we look at hypothetical networks with very randomized passenger distributions, and then we have sensitivity analysis for a lot of the characteristics of the system. So I just have it here. I'm just going to flash through it just so that you're aware. And if you have questions, we can elaborate more in the Q&A. But I just want to say, I just kind of wanted to give the intuition of this system and to show some of the results in the real world with the real world data that we had. So we were able to actually propose this type of extra long train model, which we can optimize for any demand distribution, any number of train types, any number of stations. So we kind of were able to generalize previous results from these type of systems, which before it used to be more of a one type of train type of systems in the literature. And then our case studies kind of show that really the benefit goes into around 50 to 60% benefit as opposed to kind of the 126%. But all the 126% show is that if stations are long apart, such that the headway or like the safety wouldn't be compromised by extra long trains, then you would have more benefit because you would be able to run trains at a kind of like a frequency that doesn't impede operations. And then if you are interested in the paper, we actually look at more sensitivity analysis into transfers, number of sizes of blocks, train types, and we have more insights on that. So with that, this is my presentation, and then this is kind of the paper if you're interested, and this is my contact information if you are interested in discussing this further. So thank you so much. Thank you for listening.
Thank you, Jesus. If anyone has a question, please feel free to speak or write in the chat.
The honor has a...
Hello, Jesus. Thank you for the presentation. Am I correct in understanding that basically you looked at the case study for a subway? Is that correct?
Yes.
So does that mean that the platforms don't have to be extended because the part of the train that's not being served, the wagon would be somewhere within the tunnel and therefore not require any platform extension?
Correct. I mean, this assumes that there is no further restrictions beyond the platform that will allow you, because sometimes the front part of the train is going to be the one hidden, quote unquote, and then sometimes it's the back part of the train. So we assume that those two sections would be able to just store or just have the train hidden without any kind of operational restrictions there.
Okay, thanks. Then no further questions.
And then I just want to say also, I just prepared just real quick a backup, just in case people are curious as well, is that it is true that people would have to know where they're boarding. So there is such thing as we also discussed it in the paper about this passenger information system. So you can think about, instead of taking a bus, you kind of would have like an app or something like that, or you have panels in the platform that would tell you not only what train to board, but what section of the train to board. So this is just some of the information that we identify that would be required for passengers to know at the stations. So this is something that we also discussed, which is that passengers need to be informed, which is probably one of the biggest challenges, the compliance of passengers in the system. So,
Jesus, congratulations. I really liked your presentation and the topic of your thesis and research. That's what I had in mind, as an expert in demand modeling. What would be the perceptions of the people boarding such a train, and if they would be afraid, or what other characteristics, and what which you just said regarding information is really the key answer to this, and perhaps a compatible study adjacent to yours could be something that like a state preference survey that capture the demand and the perceptions of the people utilizing such a new concept.
Yeah, I mean, we kind of rely a little bit. There's the challenge of increasing the capacity with this type of systems is that you kind of decrease the margin of error. So if you might board a train, for example, this one on the screen, you might board this block on number 1 here in this station, but it's not going to show up again until station 5. So if you're going to a station 4, you kind of we assume in this study that people will not, because this is for overcrowded systems, that the moving within the train is going to be very limited. So we don't count on that as a mechanism for serving passengers. So it is true that this would be kind of in the road to implementation. We would have to really gauge the interest and the perception of passengers for service like that. We would probably start with like a metro line, only one train type, which, as I said in the beginning, like maybe the A and B types, and then see how people react to that, to then maybe try to implement more complex protocols. Because try having a protocol of multiple train types with 5 different partitions of the train in one day, like from 0 to that, it's probably going to be very challenging. So we kind of show kind of theoretically that this is possible, and we're almost guaranteed to gain capacity. And then when I say capacity, it's not just the carrying capacity of trains, is the throughput per headway. So it's actually passengers served over time as well. So that is definitely a part of that we kind of didn't explicitly address, but then we kind of hinted when we discussed the passenger information system, or maybe the station layouts.
Thank you.
Jesus, thank you very much for the presentation. It was really interesting.
Thank you.
I have one question. I assume that we still continue to have 2 railway tracks on the same tunnel, since we're talking for underground. So are all the trains stopping at all available stations yet, or some trains may omit some stations to gain some speed benefits, maybe?
Yeah, actually, if we allow trains, so that part of the part of some of that I didn't elaborate in this type of constraints and the time constraints, is to actually exactly optimize the stopping pattern. Actually, I wanted to go here. Maybe there's not an example here, but we allow trains to skip stations as long as it is feasible within the bounds of the safety headway. We do allow trains to skip station, because that might be another way to kind of catch up if you need to. But I think some of the examples, I don't just want to flip through the whole slides, but some of the examples that I had earlier, the hypothetical ones, they do have some protocols that it just skips some stations. The same way in the current service, you might have express lines. You can also have extra long trains that you can imagine they just collect for all of the suburban areas. You just collect many passengers, and then you just go downtown, and then you start distributing the passenger. You would have to have an idea of where people are going, so be able to stagger the train to unload them in subsequent stations. So it represents definitely a logistical challenge, because you really need to integrate people's destination into account, right? So it is.
But with mass systems, mobility as a service type of systems and platforms, this would be possible.
Exactly.
Because they will have the reservations, they will have the ticket, they will know exactly where to exit. So this would be feasible, actually.
Yeah, that's what I'm hopeful for it. So we actually show in the paper, we actually show that most of the benefits that we gain. kind of in the compared to regular trends, which is kind of something that we're showing here. Not gonna go into details here. You can actually have with even with one train type and even with very few number of blocks, maybe two sections of the train only, you can already get like 30 to 60% increases in capacity. No, you don't get all the way to 100%, but you still get with very simple protocols, very significant improvement. So to me, that kind of shows that for real world implementation, it gives us hope that like it is very feasible to do in practice. Because you don't, I show some fancy, like very complex protocols, but in reality, you don't need that to have the benefit. You could have simple protocols as well.
Thank you so much, Jesus.
Yeah, thank you.
Thank
So
you.
that would
Thank
be
you
all
very
for
much.
me.
And we will move on to our second speaker, Giorgos Papaioannou. He is a researcher and PhD candidate in the Transportation and Decision-Making Laboratory at the University of the Aegean. He holds a bachelor's degree in civil engineering and two master's degrees in transportation engineering and maritime transport management. Giorgos has spent the last few years at the University of the Aegean working on the mathematical modeling of travel behavior. His main research interests focus on ferry services and their planning and modeling, as well as resilience. He has participated in several EU and Greek-funded projects and published several works in the international academic and professional literature. Giorgos, please feel free to take it away.
Thank you, Carl. I hope that you can see my screen. Wait a second. Okay, so perfect. Thank you. Thank you very much. I'm very happy to be here with you today. Thank you for the invitation. I'm going to present the research that we have carried out during the last years in our lab relevant to a scientific project named RESPORTS on the topic of port resilience. So in this project, we are a very big team. We come from multiple backgrounds. So we have the transportation background, where I belong to as well. We also have many people from the shipping and maritime economics background. We are collaborating with people from marine science and oceanography, who are also performing the simulations that I'm going to present later. And finally, we have many people from IT who are bringing together all those backgrounds into one single platform that I'm going to talk about right after. So I'm going to give some background at first, present some literature review about port resilience, introduce you to the research questions. I'm going to talk about our approach, which is living labs, and the development of a metric to measure, to quantify resilience of ports and to be able to compare different ports in terms of resilience on a quantitative basis. And finally, some results, discussion, practical implications, and so on. Maritime ports, as you may, it is obvious that they are critical infrastructure. They have a very important role. They are vital for functioning of society and the economy. Maritime ports provide services that, if disrupted, this may have a very significant impact on human living, on public health, on safety and economic stability of the country. But guess what? Their geographical position renders them very vulnerable to extreme weather events. And there are several examples of such extreme weather phenomena. For instance, for the United States, I can mention New Orleans. It's one of the most well-known disasters during the last years relevant to extreme weather, the Hurricane Katrina. Also Hurricane Sandy in the ports of New Jersey, New York. Hurricane Harvey that hit the port of Houston some years ago. And the economic impact of such storms could be really negative. There is research indicating that a Category 1 storm hitting a port may have similar effect on exports from unaffected US states as a 4% ad valorem tariff. And although 4% may sound negligible, believe me, it's not. It's huge. So there is an urgent need for proactive resilience management in the port industry, and our research aims to contribute towards that direction. We are a country that we have more than 250 inhabited islands, the majority of which have a population less than 1,000 people. We have 154 ports and many links connecting those ports. You may see the significance of each port compared to each other in this figure. So, node size indicates passenger throughput, and color indicates degree centrality of each of the port. An additional challenge is that for the majority of those ports, almost two-thirds of them, summer traffic accounts for more than 50% of the yearly traffic. And this introduces additional challenges to resilience, as any disruption during the high demand period may have very important economic consequences as well. A port, in general, is a system. It is composed of multiple interconnected subsystems that interact with each other. A very generic representation of a port as a system is demonstrated in this figure. So, for instance, there is the port itself. We have the interface of the port with the open sea, including all those operations of the port towards the sea, such as navigation areas, access channels, maneuvering areas, berths, and so on. We also have the port hinterland interface, including the transportation networks, the infrastructure that connect the port with its hinterland. And we have the port itself, which has mainly two components, the infrastructure and the superstructure. Infrastructure includes the quay walls, the mooring equipment, all those things, while superstructure includes the mechanical equipment, warehouses, electricity facilities, whatever is over the ground. And of course, this leads us to one realization that since a port is a system, it is as resilient as its weakest subsystem. So it is like a chain. The overall strength, let's say, of the port is determined by its weakest subsystem. Port resilience refers on the ability of a port to adapt to a new normal state after disruptions. And according to the United Nations International Strategy for Disaster Reduction, resilience can be categorized into four levels. Of course, the worst case scenario is collapse, where the port fails entirely. If a port can cope, then it manages to recover, but at a degraded state compared to the normal state. The third level of resilience is the recovery. It's a more favorable outcome where operations may return to their normal state. And finally, the highest level of resilience is adaptation, where the port is able to return not only to its normal level of operations, but also to be able to withstand the same disruption in the future and being robust to them. But achieving this level of resilience, achieving adaptation, requires collaboration among multiple stakeholders, which in many cases they may have also conflicting objectives. And this is what our research tries to achieve. There are several works in the academic literature that promote multi-stakeholder collaboration methodologies. In our research, we are introducing a methodology that is very well known to urban science, living labs. Living labs are actually user-centered open innovation ecosystems where real-world experimentation and innovation take place. Living labs aim to bring together multiple stakeholders from, in this case, the port industry, on the following objectives. At first, they are real life environments. They aim to enhance user involvement. So users actively participate in the innovation process and co-create solutions. Living labs are actually environments in which experimentation take place, and there is iterative feedback about the innovations that are developed. And that's the most important compared to other methodologies, that the solutions are improving and improving forever and ever. So our research questions are: what insights emerge from port stakeholder survey responses across the living labs that we are establishing? Based on this, can we develop a metric? Can we develop a key performance indicator that measures port resilience? And how can we do so? And finally, based on this, can we develop also a decision support system that aids decision makers with making decisions about making their entities more resilient against extreme climate events? Living labs take place into different phases. So the first phase is planning, then acting, and finally executing. The first question is where to establish those living labs. So some kind of geographical clustering has to be performed. We did it with the K-means algorithm, grouping Greek ports on 14 different groups based on their geographical proximity and network characteristics. And then we are choosing 3 different areas: the region of Thessaly, in which there is recent experience from extreme weather, the cyclone Daniel, which also had many fatalities. We are also choosing the region of North Aegean, Chios, and the islands around Chios, due to the social impact of the port of Chios at this region. And finally, Crete, the port of Heraklion, due to the importance of Crete as both an agricultural region. The majority of agricultural products consumed in Greece and the Balkans are produced in Crete. And also Crete is an island where there is very important tourist industry. And so we want to assess the resilience of the port serving this region. Here you can see the location of the three living labs that are established. We have about 60 representatives from different stakeholders participating in those living labs. We have representatives from first responders, such as the police, the port police, the fire brigade, port authorities, academics. We have many people from the civic society, from the shipping industry, and finally from local governments. We are using the quadruple helix model of participation in our living labs. So I talked about Volos. This is the impact of the cyclone Daniel in Volos. The port had to stop all kinds of operations for many days after this storm. And there is also long-term impact. all the railway network was completely destroyed. So the port now is not connected through railway with the rest of Greece. And also, due to the materials that were brought by the three rivers that end within the port area, there is a lack of depth at the moment for cruise ships that need to call at the port. So many cruise ships are not able to call at the port of Volos, even now, 1 year later, 1 year after this event. So at first, we are asking the stakeholders which are participating in the living labs, how critical do they perceive different climate hazards? We are assessing 7 different types of climate hazards, which is rain-induced flood, sea level rise flood, heat waves, storms, extreme winds, snowfalls, and extreme waves. So as you may see, for some of the ports, the stakeholders do not perceive sea level rise flood as an important threat. However, there is a mismatch between stakeholder perception and the actual results coming from simulations. So those are flood inundation simulations that were performed for the context of the living labs by the marine scientists that are participating in the consortium. And here, as you may see, for the port of Volos, numerous building blocks are flooding. An important part of the port is also flooding. This is for a storm, a 10-hour duration, a 10-hour storm that takes place, and under the RCP 8.5 scenario. So each run of the model simulates such a storm. The different colors represent, of course, different water depths. You may see something similar for the port of Chios. Chios is also the location of our department, Civil Traded Transport at the University of the Aegean. So this is where our department is located. But you can see here that it is very important to mention that there is a master plan at this port for further development of the infrastructure that does not take into account such climate hazards. So as you may see in this region, that it's going to flood under this specific scenario, it is planned to develop a new ferry terminal. So you can see that in the context of the living labs, such risks are identified and adaptation measures are developed. The port of Heraklion appears to be more resilient than the previous two. There is only minor flooding in some specific areas like the Kule in this region. This is a medieval castle. So based on the previous, we are developing an index and a KPI. We are using the multiple criteria decision aid framework to develop this index, and more specifically, the analytical hierarchy process. We are defining 4 levels of hierarchy. So the first level is the index itself. The second level has to do with distinct impact areas that affect resilience. Each impact area then is characterized by a number of criteria. So the first impact area is infrastructure resilience, and it is characterized by physical infrastructure resilience and climate change resilience. Operational supply chain resilience, the second impact area, that is characterized by operational resilience and supply chain resilience, digital resilience, socioeconomic and environmental resilience, and finally, governance and compliance resilience, which has to do with the governance practices that are followed by the port. we are taking input from the experts in order to establish priorities among the different impact areas and criteria. For each one of the hierarchy levels, we are developing a priority matrix where the elements of the matrix are the geometric mean of the input of the participants of the Limit Lab, and the final weights are calculated as the normalized eigenvector of the priority matrix. Of course, this method, the analytical hierarchy process, that it's the most frequently found in literature method of the multiple criteria decision aid systems. It was established by Thomas Lorisatti at the late 60s. There is one limitation in that method, the consistency ratio, which we monitor it and we make sure that we are within the limits, less than 0.1. So here you can see the final weight that is assigned to each one of the impact areas. The most important impact area occurs the infrastructure resilience, and the least important is the digital resilience. The second most important is operational and supply chain resilience. And also, each criterion is getting also its own weight subject to its impact area. And based on this and the performance of each port at the indicators of the criteria, which is also obtained through experts' input. The participants of the Living Labs are giving us the data about the performance of each of the port relevant to the indicators of the PRI that we are developing. We are able to calculate finally this KPI. So for the three ports that we are assessing, Volos is the most resilient, whilst Chios is the least resilient. The actual objective that we want to achieve through this port resilience index is to develop a decision support system. As I mentioned, there is a mismatch between the perceived severity of climate events and the actual severity that is occurring by the simulation models. So, what we want to achieve is to develop an AI-based tool that it is currently under training that may have many functions. So the most important are evaluation of individual port needs of the port that we are assessing, identifying similar ports and best practices through relevant reports, proposing adequate resilience measures, and finally, receiving feedback about those measures and iterative improvement of the solutions that are proposed. This may be achieved by several techniques. So at the moment, we are using LNP, natural language processing models, but we want also to develop purely quantitative models for this purpose. Here is the user interface of the decision support system that we are developing. Okay, excuse me for the Greek, but it's a tool that analyzes the different aspects of resilience as presented in the Port Resilience Index. So living labs have significant benefits to port resilience compared to the traditional approaches, as they are iterative processes that provide continuous feedback on the co-design and innovations. And they also provide the opportunity to discuss between the research team and the involved stakeholders in a systematic way and in a solid framework in a well-defined environment. The KPI that we're developing is an attempt to measure the resilience of Greek ports and to evaluate, to compare resilience on a quantitative basis. We are trying also to combine this with other research. So, okay, port resilience is very highly related to logistics and trade and also to passenger transport, but it's not only related to this, it plays a critical role as well in disaster response and evacuation planning. And you can see it through these examples, for instance. So in the last month, we had some very strong earthquake activity in Santorini. It is estimated that more than 15,000 people evacuated the island. Another example is the Mati wildfire in East Attica during the summer of 2018. There were, if I call well, 104 fatalities at that wildfire. So the port of Rafina had to play an important role in evacuation of that area during that wildfire. So what we are doing is that we are modeling individuals' behavior during extreme events. We have already collected the relevant data. Here you can see, for instance, a flowchart of the survey that we are using for collecting this data. So, okay, at first we ask them for their consent to participate. We ask them about their past exposure to physical hazards. And if they have survived an important life-threatening event, we also use some psychological, we also perform some psychological evaluation of post-traumatic stress and experiences. We are using stated preference scenarios about evacuation. And we are developing models about their behavior and their mode choice during such events. We are planning to add such a component in the developed decision support system for the Greek ports. So that it is complete. It includes both supply, anything that has to do with the port infrastructure, but also demand during such events. Here are some relevant publications from the project. The last one is very recent. It is, I think, February 2025.
Because I don't mean to interrupt. I just wanted to give perfect timing. Wanted to give an opportunity for the audience to ask any questions because thank you so much.
Okay.
Great presentation.
Thank you very much. Thank you.
A quick question. I think in a lot of the examples that you discussed, you were telling us about the hazard that you were looking at was flooding and how it might impact the direct port operations. And you also told us that you were considering some of the back end, like both the port itself and also the hinterlands and so on and so forth. And so I was curious how far along you were in terms of thinking about some of the other hazards in that might affect this upstream operations.
Well, actually, I have demonstrated flooding, but we also considered any other hazards, not only flooding. But in the context of a 20-minute presentation,
it was perfect.
Yeah.
No, thank you. It was perfect, Giorgos.
Thank you.
Before we end, I wanted to thank both speakers. I don't have another question. Let me interrupt. But so I'm in advance thanking both speakers. I think that excellent talks and wonderful to bring together people from all over the world, even though it's unfortunately virtual. Yeah. And nice to meet you virtually, Professor Amalia.
Nice to meet you too.
Nice to
I
meet you.
wanted to add also that one of the big threats that we're going to see in the future is because of heat waves. So this is something that we are also studying because we will have in the simulations that we are doing show that in the next 40 years we might have like 6 to 8 hours only that we will be able to go outside of home, and then all the rest of the time to be inside. So, and this also for the port operations signifies a lot of a very big hazard. And this is something combined with the floods that Giorgos mentioned. It is something that we should study in more detail.
Especially in the living labs, the stakeholders mentioned about the heat bulb effect, which is actually a very important practical limitation in port operations. So there may be many hours of the day that any kind of external operations in the open, not inside the building, may not be allowed due to extreme temperature and extreme humidity. It's not about temperature only, it's about the combination of temperature and humidity that imposes the risk to human health and the port operations. So I demonstrated very extensively flooding, but we considered 7 types of climate hazards. Yeah.
Yeah, it's kind of interesting in transit systems. People are starting to look at the measures of exposure too, because of that. Like not only travel time, but it's like how much are you exposed to this type of extreme weathers when you're waiting for transit, for example. So it might be something very related where you have to design to minimize not only travel time, you might need to minimize exposure. Maybe people have a longer travel time, but you minimize exposure to the outside due to extreme heats. You know.
I think they are doing something like this in Singapore.
Mm-hmm.
Yeah.
So it's very, very related to that. Very interesting talk. Thank you.
Yep.
Thank you.
Well, if there aren't any more questions, thank you everyone so much for joining, and thank you for the presentation. It was really great.
Thank you very much.
Thank you both.
All right.
Thank you.
Thank you all. Thank you for the
Have a
invitation.
nice evening. Bye.